So good evening everyone. Let us get started with our today's discussion. I'll be going through a brief recapitulation so that I can start the model of decimation. We have covered all the individual parts, so I'll go through the individual parts one by one very quickly. So we started with a two-pole decimation model with some 12 slots, and some details we had put that we have 50 conductors per slot. Then after that, if we saw that if we excite the field we excite the field with some current, that is the field winding is excited, then this is how the flux lines look like. And if the rotor is made to rotate, then we see that the flux linkage or the flux distribution remains almost the same. And we went on to see if the time variation, so the current is fixed but the flux rotor is rotating. Because of that, we saw that flux linkage of the field winding is also is varying uh, a little bit, but mostly it's a steady quantity. If you see, this is this point is 3.25, and so you can understand that it's almost a DC quantity with a small ripple, and that ripple is related to the number of slots that we have. So we saw that we understood that why that varies because of rotor position. And finally we understood that the flux linkage of the field winding is almost constant with a small ripple, and if the number of slots is increased, then even this ripple magnitude will also go down. As well as the if we reduce the slot opening, so if we make the slot very much semi closed with a very small narrow gap at the tip, then this variation will reduce significantly whatever small variation we have. So we know that the inductance of any winding is basically the flux linkage. The self inductance of any winding is the flux linkage due to its own excitation. That is, if current is excited, then whatever is the self flux linkage in the self inductance is the ratio of those two, that is self flux linkage divided by current. And we saw that but the dependence is very weak. So this can be considered approximated to be a constant quantity. So this comes out that LF, although it is a function of rotor position, but that can be approximated to LF, a constant quantity only. And you know that any winding will have some resistance. So the we have the we can describe the field winding as a series combination of some resistance that represents the IR drop and a constant inductance, that is LF. So we saw the how to model that. Next we came to the modeling of the armature coils. We saw that if we excite the field winding in the stator and make the rotor to rotate, then flux linkages of all individual coils, they actually vary as shown in the right hand side figure. So they are constant for almost some time, then they vary then they increase linearly, then they remain constant for some time, again they reduce linearly, and again they remain constant. So this is how flux linkage of all individual armature coils vary with time. So we understood that rate of change of flux linkage is nothing but induced EMF. So if we see in that sense, some positive induced EMF will be appearing across that coil in this duration, and some negative induced EMF will be there in the other in the falling region. So that's a flux linkage, that's an induced EMF that is quasi square wave in nature for all individual armature coils. And additionally, we understood that if this is the coil, say this is the coil, then the coil axis is the stator poles, so effectively a very small air gap. But if after some rotation, if the same coil appears there in the interpolar axis, then it is the coil axis is the large air gap. So that means with rotor rotation, the individual coils, the reluctance in by the individual coils, they vary quite a lot, and that would cause the armature self inductance will also to vary and be a function of the rotor position. So this is the armature coil. So the armature coil, all individual armature coil inductances, they are basically functions of rotor position. But if we just remember our DC machines course that I think all of us have taken, we remember that the DC machine, the steady state equivalent circuit of the DC machine includes only some resistance that will be anyway there to model the copper loss, and it has some constant back EMF. And we can understand that in the transient case, it will also, any coil has some inductance, so that there will be some inductance also. If you have taken the drives course also, you know that the armature winding is also modeled with a constant inductance. So the question that we asked is, we understand the individual armature coils, they have the inductance varies with rotor position, as well as the induced EMF is not constant, it is a quasi square wave in nature. So to understand that better, what we did, we understood the armature winding, how it is done. We understood the commutator, how commutator brush arrangement makes or how that is done. I am not going to discuss that to details in this lecture, because we have already spent some time discussing that. But we understood that what eventually we understood the commutation as well. But what eventually happens is um, the number there are parallel paths formed because of this commutator and brush arrangements, and some of the coils come in series, and some of the combination of those coils come in parallel. That is what we know. We have heard the term parallel paths, number of coils, some coils, and all the coils have some induced EMF. And if we look at the flux linkage changing, um, so the coils which come in series are basically these coils. So if we remember, for this rotor position, these coils actually come in series, and this pink coil undergoes commutation. So we understand that this green, orange and blue coils, they are having some positive, some non-zero induced EMF which come in series, so which add up because they come in series. And for the next rotor position, so that is say this rotor position where none of the coils are actually undergoing commutation, then all these coils, they come in series. But the induced EMF of the coils which are not directly under the pole, they are negligibly small. So in this case, we can see that we have four coils coming in series, say induced EMF of them are equal, so we have some net induced EMF in the armature coil. So we saw that it actually varies with time, based on whether any coil is undergoing commutation or not. So for the earlier case, if say three coils are having non-zero induced EMF, we saw say 10 volt per coil if this is the induced EMF. And in this case, four coils are um, having non-zero induced EMF, again 10 volt per coil, so we have 40 volt. So we understood last class that if we have more number of slots, then this small ripple between 40 volt and 30 volt that we have in the induced EMF, that also could be reduced, and the ripple could be made negligibly small for if the DC machine is designed well, taking care of all these things. So this is so we understood that the commutator and brush arrangement, how the different armature coils get connected in series and parallel way, that makes the quasi square wave induced EMF that appears across all the individual coils uh, into into a DC constant DC quantity across the two terminals of the brush. So this is the are these are the two terminals which basically come out to the external world, where we connect some DC source, where, or if it is generator, we connect some resistance to take out the power. So this current, if we see, or if the machine is made to rotate, if we measure this induced EMF, we will see that this induced EMF will be reasonably a constant quantity, which of course depends on the field excitation. Why we discussed, because the field excitation basically decides how much will be this flux, that anyway will discuss as we go forward. And the induced EMF is constant, how we understood. And next thing is the armature inductance. So the net inductance of the armature coil, all the coils, if they are not so in this case all these coils will be carrying say dot current, and all these coils will be carrying cross current for this rotor position, where none of the coils are undergoing commutation. Next, where one coil is undergoing commutation, then that coil is not part of the circuit, but the other coils, the other top coils, they will be carrying dot current, and these coils will be carrying cross current. So uh, this is the scenario that we have. And we can see that all these coils, although as the coils rotate the inductance varies, but no matter what, all the top coils uh, will be carrying dot current, and all the bottom coils, they will be carrying cross current, based on whether it is motoring or generating. This dot and cross current can reverse, but this is the case for all the cases. Similarly, for this case also, all the top coils are carrying dot current, and all the bottom coils are carrying cross current. So what is the magnetic axis? Magnetic axis remains fixed for both these two variations, and both these are the only two variations, and in between something so, yeah, these are the two extreme cases of rotor position between which the cases change. So so this is for both these cases the magnetic axis remains the same, so the reluctance also remains the same. And number of turns, if we have quite a lot number of slots, and we have reasonable number of conductors in everything, then um, it is possible. So again, based on rotor position, it will be varying little bit. But because in two cases, in this case at least, where the commutation is happening, then the number of turns that is there in the armature coil, that is reduced, because this one set of coil is not actually coming in the series path. But in this case, all the coils are coming in the series path. So you understand that there is some change in the number of turns. Um but if the coils are designed carefully, then even and if we have enough number of slots, then even this variation is not too much. So although the armature inductance is strictly speaking a function of rotor position, but this dependence is quite vague, so it can be approximated as a constant quantity. And already we have seen that the back EMF as seen from the two terminals of the brush is a constant quantity. So if we try to write down the equivalent circuit, if we want to model the armature winding as a equivalent circuit, then obviously we need to put some resistance to model the IR drop. Then we have to put some inductance, that is the armature winding inductance, that we saw that although this is dependent on rotor position, but it can be approximated to a constant quantity. And again we have we have back EMF, so this this E is again uh, uh, may change with rotor position, but if it is again designed well, the ripple is quite small, so this also can be approximated to a constant quantity. So this becomes the equivalent circuit of the armature, where this is the input voltage VA that we give. So if I write down the equation, this is RA. So the equation, dynamic equation is VA equal to, if say IA current is flowing, so it will be RAIA plus LA DIA dt plus E, say let me say back EMF, so EB. So again, this is this is a linear differential equation with this is a coefficient and this is a coefficient of the differential equation. Both these are constant, so it is a linear time invariant differential equation. And this is a back EMF, uh, which is the back EMF. What is that? Back EMF basically depends on back EMF is proportional to the field current, and also back
And
EMF is
speed.
proportional to the speed, right? So we understood why it is dependent on field current and why it is dependent on speed from the flux linkage variations. We have already seen that. So if we want to model if we want to get a model for the armature winding, then our input is basically VA. From there we will have to subtract the back EMF. From there we will again have to subtract the IR drop, say IARA. After that we have uh, so what I am doing, VA minus EB, that is equal to, so VA minus EB equal to IARA plus LADIA dt. That is the first step I have done. After that, if I subtract the IARA also from this whole thing, then we have VA minus EB. From there, I am subtracting IARA also. So what I have is LADIA dt. So if I multiply by 1 by LA, then only thing I have is DIA dt. If I take a integration of that, then what I have is IA, and this IA has to be multiplied by the inner resistance to feedback, and subtract the IR drop from there. So this is the model. So this is the model of the armature winding,
Sir, can't
where
we write it in the form of S plus SLA plus RA?
we will understand when we can and when we cannot, and
Okay,
what
okay.
is that representation, that also we'll discuss. But this is directly coming from the differential equation, that
Yes, yes,
is
correct.
from Laplace transform. Laplace transform may not be holding good for certain cases, like that only holds for linear time invariant systems. If it is time variant or if it is non-linear, that may not, that type of representation will not hold. So this is the most general representation that holds for all the cases, right?
Yes, sir, correct. Thank you.
So so this is the mathematical and equivalent circuit model of the armature winding, and this is how uh, we can we can solve it. If we have the input and if we have the back EMF known, then we can solve for the armature current. Now DC motor, any electrical machine, that is not only an electrical system but also a mechanical system. So what are the so any mechanical rotating system, if it is a rotating machine, so what are the related quantities that we need to be worried of? So say we have a rotor that rotates at certain mechanical speed, say omega m. Suppose so in order to make it to rotate, just like if we have a body of mass m, and uh, if we want to move it at certain pace, then we need to apply some force. If we need to apply some force in order to make it to accelerate, right? So similarly, for a rotating body, we need to apply some torque in order to make it rotate. So if it is a rotating, so if it is a machine acting as a motor, then electrically we have to apply the torque that will have to oppose the inertial torque, that is the opposition that any gives, that any body, the Newton's second law, that any body, second law or first law, yeah, forgot anyway. So anybody tries to be always stationary, and it will be opposing any change of velocity. So that is basically the, what
Inertia.
is that, the inertia. So any rotating body that will oppose its change of velocity, it will always try to, if it is a frictionless system, then it will always try to rotate at the same speed, and it will try to oppose any change of speed. That parameter is basically the
Moment of inertia
inertia.
in case of circular motion.
Yes, in case of rotation, it is polar moment of inertia, to be very specific. So, so that is represented by J. So, if a body is quite big, then its J will also be very big. That means we need to apply larger torque to make the speed change. So any change of speed is represented by d omega dt, the rate of change of speed. So the torque that we need to apply to to change the speed at certain rate, that is the proportionality constant is basically J, the polar moment of inertia. So if we have a rotating motor, then it will certainly have a polar moment of inertia. That means if we want to accelerate or decelerate that, if we want to accelerate that, then our applied torque needs to provide that component of torque. Now additionally, what else will be there? For any practical system, there is some friction. So friction is something that will try to oppose it. And um, for a more simplified case, the frictional torque can be, the frictional torque, say F friction, is generally considered to be proportional to speed. It is a damping torque. So the proportionality constant of frictional torque can be represented with B. So it becomes B omega, Tf equal to B omega. It may not be holding for some other type of systems where frictional torque can also be nonlinear, but for most mechanical systems, low speed systems, this relationship holds good. So the frictional component of torque is proportional to speed, and the proportionality constant B is known as frictional coefficient. And additionally, when a motor is rotating, that means the goal, so this J d omega dt torque, the motor needs to provide only when it is accelerating or decelerating. The frictional torque the motor needs to provide always, but the purpose is to do some mechanical work, that is the load, that is to drive some load. And the load, suppose we are having a motor, and that is connected to a pump. So we have a motor, we have a pump. Now whatever work the pump is doing, that will require some power, that will require some mechanical power. And if the motor is rotating at reasonably constant speed, then whatever power the pump requires divided by speed is basically the load torque the pump draws, or pump requires from the motor. That means, and this load torque, if it is in the motoring action, this load torque also opposes the electromagnetic torque that makes the motor to rotate. That means if we have a motor, if we want to rotate in this particular direction at a speed omega, then what all torques are there? We have a frictional torque, that is opposing it. So this is b omega torque. We have load torque that is also opposing the rotation, and we have electromagnetic torque that is causing this rotation. And the j d omega dt torque that will not appear in the steady state where the motor speed is constant. That will appear only when omega there is some change in omega. So that we will not worry about that in the steady case. But in the transient case, if we want to write the differential equation, then T electromagnetic is basically j d omega dt plus b omega plus load torque. So this becomes the dynamic equation for the mechanical plant of the DC motor. So you can see in this way. Suppose the motor is rotating at a constant speed. Motor is rotating at a constant speed. Say these are the other quantities. So if motor is rotating at a constant speed, then the frictional component of torque, say frictional component of torque T friction, will also be constant, right? What will be the inertial component of torque Ti, that is j t omega dt, that will be 0. And load torque will be anywhere there. If load torque is there, it will be, the load torque will be there. There will be some load torque. So what will be the electromagnetic torque? Electromagnetic torque will be the addition, sum of frictional torque, inertial torque, and load torque. It will be the sum of these three quantities. Now suppose I want to uh, increase the speed to some other speed. So I want to change the speed. Say I change the speed linearly and reach another speed from omega 1 to omega 2. Now in this duration, the frictional torque, because it is proportional to speed, it will also change. It will basically scale up. So it will basically scale up. These things are not to scale because frictional torque will be a very negligible quantity of the whole torque, but I am only showing them exaggerated to get a sense of what is happening. Now inertial torque, because that is proportional to d omega dt. D omega dt is constant for this duration. So d omega, say d omega dt is constant at some value in this duration, and that multiplied by j is this torque that it requires in this duration only. And after that, when the motor speed has reached steady state, then again this inertial torque will be 0. And load torque, say load torque demand remains the same. So what will be the electromagnetic torque that will be drawn from the motor for this type of a scenario? If I draw that on top, so this is the electromagnetic torque that is required from the motor. So for the first duration, it is the sum of whatever Tf plus Tl, say this value. In between, some inertial torque also comes, mechanical torque, frictional torque also increases, and load torque is as it is. So there will be a step jump, and even that will be, if this frictional torque would not be rising, then it would be only a constant quantity. But because the frictional torque is also rising, so it will also slowly rise in this duration. And after that, what will happen? It will again, whatever is the frictional or this inertial torque component, it will come down by that value, and the torque will continue to remain like this. So this is the torque. This is the kind of torque that will be required to change the motor speed from initial speeds omega 1 to omega 2, right? And how quickly we need to change the speed, that depends on how much overload so how we can change the torque of the machine. So again, that will be part of control, how we design the speed controller to change the motor speed quickly uh, from one speed to another speed. And suppose what happens if we now decelerate. If we now decelerate, say we now decelerate the torque, we want to decelerate the speed from this values to linearly, because linearly d omega dt calculating that is easier. So I'm assuming only linear cases here. So say the speed now needs to reduce from omega 2 to omega 3 like this, and again remain fixed to remain fixed at omega 3. Now what will be required there? uh, so in this duration, the because speed is falling, the frictional torque required, that will also fall, and that will fall to a value lower than the initial value, because the speeds are the omega 3 is lower than omega 2. So it will come down like this. The inertial torque will now become negative. Inertial torque will be negative, and load torque, say, it remains the same. Now what will happen? It will be reducing. So it will be so some load torque is already load torque remains the same, positive. There is some negative inertial torque, and there is some falling this frictional torque. So anyway, it would be like this. If had it been only had the frictional torque not been significant, but because frictional torque is also there, so it will be like this, and after that it will continue. So this will be the electromagnetic torque. And you understand that if we make the load torque 0 during deceleration, then we have the load torque, the electromagnetic torque that we have, that would be negative. If this inertial torque is very high compared to the load torque and frictional torque combined, then it is possible for us to get generation during the deceleration period. So that is what is known as regenerative braking. When you brake the motor, and the motor does not, and the load torque is very insignificant, and we decelerate the motor, so that the electromagnetic torque actually becomes negative. If it becomes negative, that means for that duration, power is not drawn from the electrical side to the mechanical side, but it is going back from the mechanical side to the electrical side. And if we have a power electronic converter that can that can take some power current back, then that current can basically come back and charge the battery, and that can store the energy can be stored in the battery. So that is what is known as regenerative braking. But if we now want to get the mechanical plant model, so what is the input of the mechanical plant model? Mechanical plant model input is the torque, the electromagnetic torque. So we have the electromagnetic torque, that is the input, Te. Now we have to subtract the torque, load torque demand. We also have to subtract the frictional torque, that is B omega. Then we have to uh, divide it by J. Then we have to integrate to get omega, the speed, and this speed has to be fed back and multiplied by B, and that will form the mechanical subsystem, mechanical plant model of the DC motor. So this is the mechanical plant, where we have torque, electromagnetic torque as the input, load torque as one of the disturbance inputs, and speed as the output. So this is the mechanical plant model of the DC motor. Now what about electromechanical energy conversion? So if I quickly go to the dynamic equivalent circuit model of dissipation that I discussed long ago. So this is the field circuit. We have the LF, the field winding inductance, RF, the field winding resistance. We have the armature winding, that is we have the armature winding inductance, armature winding resistance, and some back EMF. So this is the armature circuit, this is the field circuit. And what about mechanical? So motor tries to rotate at omega in this duration. So basically the retardation, the load torque will be opposing that, the frictional torque will be opposing that, and j omega dt torque is anyway not shown here. I'm not sure what this TD is, so let us neglect it for now. So there will be some opposing damping torque, obviously. I think okay, let us ignore that. So the electrical field circuit is anyway, um, we know this is VF. The field circuit is basically VF is the input, IF RF plus uh, LF DIF DT. So this is the field circuit model. Armature circuit model is this: VA equal to LA DIA DT plus RA IA plus EB, and mechanical is TE equal to J D omega DT plus B omega plus TL. TL is load torque. Now, the electrical and the mechanical equations, they basically interact. How do they interact? They interact like this, as I have shown here. The current is related to the torque by this relationship TE equal to KIA. And again, this back EMF is dependent on the speed, that is solution of this mechanical system. So mechanical system, whatever omega m is solved, that has to be multiplied by some k, some gain, to get the induced EMF, and that will be fed back. So electromechanical energy transfer is nothing but how a variable in the electrical circuit, namely IA, is related to Ia is related to the electromagnetic torque, and how mechanical quantity, say omega m, mechanical speed, is related to the back EMF. So this is the electromechanical energy conversion. And how are they related? If we remember, the torque is basically some constant into flux per pole into armature current, and again back EMF is some constant into flux per pole into the speed. And what is this flux per pole? Flux per pole will discuss in some time, but flux per pole basically depends on the field winding current. So this is how this field circuit decides what will be the gain given by this electromechanical energy conversion system. So basically we have four things simultaneously running. One is this field circuit, another is the armature circuit, another is the mechanical circuit, and connecting the electrical and mechanical circuits, we have the electromechanical energy conversion, that whose gain is decided by the field winding, right? So uh, so let us try to understand what is flux per pole, and what is so yeah so what is flux per pole, let us try to understand. So this is the this is a cross sectional view of a DC machine. This is the field winding. So say this is dot, this is cross, again this is dot, this is cross. So because of this kind of field excitation in space, there will be some distribution, B distribution, there will be some flux lines, and those flux lines will be coming out and linking the rotor winding. So there will be some B distribution in the air gap. So if I draw a air gap circle, I have already shown how the B as a function of theta, say this is the point, so this is any arbitrary point, the angle of that is say theta space, this is the space angle. So how B will vary with theta space, we have already seen. It is almost constant under one pole, and again the opposite polarity constant under the opposite pole, and in between it takes a bell shape kind of a thing. Now half of that, if this is the interpolar axis for the field winding. So this is 0, this is 180 degree or pi. So if we integrate b from 0 to pi, then whatever we have, the area enclosed by this b theta curve, that will give us the flux per pole. And you can understand that this b, the peak b that we have, that directly depends on the current, the field winding current that we with which we excite. And up to some extent we have discussed in the last class. Okay, so here I have drawn the flux linkages of the armature coils as the rotary rotates. So what is this flux linkage? If there are some Na number of turns in armature coil, so Na multiplied by phi p is nothing but the peak flux linkage of the armature coil. What is the peak flux linkage? Here this is the peak flux linkage of the armature coil, and again this value is the peak flux linkage of the armature coil. So this value, and again this positive value, is also the peak value of the flux linkage. So this is plus psi peak of armature coil, and this is minus psi peak of armature coil. So as the rotor rotates, the flux linkage of the armature coils, they vary in between plus psi peak and minus psi peak, and the psi peak is related to flux per pole by simply multiplying it by number of turns. So this is how the induced EMF, we have already discussed last class that induced EMF, because induced EMF is d psi dt, so because it is multiplied by Na and psi p, so and phi p is dependent on current, so the induced EMF is dependent on field winding current, and it is also dependent on speed, because whatever this rate of change, if we rotate faster, then this rate of change will be higher. If we rotate slower, it will be lower. So that we have already discussed that how induced EMF is dependent on the field current as well as the speed. But now let us try to understand the relationship between flux per pole and field current. Now we have already discussed that there is, for any ferromagnetic material, there is something called as BH curve. There is something called as the magnetization curve or the BH curve, where till some point called as B saturation, the B and the H, they are proportional to each other. That is, this curve is a straight line, but beyond that it is not a straight line. That is, even if we increase H by larger quantity, B will not increase linearly, but it will increase slowly. Okay, so if we excite the field winding with lower amount of current, so that the B in all parts of the magnetic core is within this B saturation limit, then whatever then uh, this P, then this flux per pole, that is this area, that will increase with field current in a linear fashion. So if we have this flux per pole, which is nothing but integration of 0 to pi b of t theta, so that is basically some scaled version of flux per pole. If we multiply it by area also, so some radius into some axial length, if we multiply it by that, then we will get the flux per pole. So if our field current is lower, if the field current is lower, then if we the field current and flux per pole, they are linearly related, so they increase linearly. But beyond some field winding current, where the B distribution in the core, in the stator as well as in the rotor, exceeds this B saturation limit, then what happens? Then this, even if we increase the IF by larger amount, the flux per pole does not increase uh, proportionally, but it increases slowly. So this will become nonlinear. This relationship between flux per pole and current, they will not be a straight line, but it will be a nonlinear curve beyond a certain value of maximum flux per pole. So the flux per pole versus current would look like this, and this is the most significant nonlinearity that exists in any electrical machine, which cannot be avoided. So next what I will discuss is first the linear model of a DC machine. First the mathematical model, the differential equations, I'll combine them. Then I'll discuss how to get the DC machine model, a linear model where firstly we will operate only in this linear zone of field current and flux per pole, and then after that uh, we will go to a if we want to incorporate the nonlinear model also, then we will go towards that. But before that, just before that, what we will discuss is how this type of nonlinearities are typically handled in electrical machines, because linear relationships can be handled by writing differential equations, and that can take care of all the dynamics. But if we have some nonlinearity, then we need to get some characteristics that will what we mean by linearity and nonlinearity. If we have two variables, say here, uh, obviously this flux per pole, that is a variable that depends on the field winding current, and the flux and the field winding current, and flux per pole, these two are variables. And if we have seen their relationship, flux per pole and field winding, they are linearly related up to some lower value of field current till the time the machine does not saturate. So till that time phi p can be written as some constant, say constant k1 into if. Then these two, we have two variables which are scaled version of each other, so it is a linear system, it is not a non-linear system. But if we have two variables which are not related by a constant scaling factor, but by a nonlinear relationship, where beyond certain value of field current, the relationship does not remain linear. That means um, uh, there is some non-linearity in the system. Then how is this handled? Is we will get these characteristics. Get these characteristics separately. How the flux per pole and if varies with each other. We will get that characteristic separately. Now flux per pole, if we want to do experiments and get that getting flux per pole is not that simple. But what is that quantity that is directly related to flux per pole? It is the induced EMF. So a back EMF or induced EMF is a scaled version of flux per pole and speed. So if we run the machine at a constant speed, so in open circuit characteristics, what do? We run the machine at a constant speed. So we have a machine. We run the machine as a generator. So we have a separate motor that runs the motor at a constant speed, and we have the two armature terminals open to us. We measure what is the induced EMF there, and we keep this open so that there is no current flow. So Ia is equal to 0. If Ia equal to 0, then La dia dt, that is 0, and Ra into Ia, Ra into Ia, that is also 0. That means this induced EMF we can measure the induced EMF directly, because there is no current flowing. So these components, the inductive drop and resistive drop, are 0. So we can get a measure of the induced EMF. So say we excite the machine field, there is a separate field winding. So for some induced EMF to exist, we need to excite with some field current. Say we give some field current, we measure some induced EMF. So this is EB versus IF. So for some field current, we get some induced EMF. We we excite the machine with a different field current, we get a different induced EMF. We excite the machine with a third field current, we get the third induced EMF. Like that, we do this experiment for certain cases and we get some characteristic like this. So this is the open circuit characteristic of the DC of the DC machine at that particular speed equal to omega 1. Now if we do the same experiment at multiple speeds, if we require multiple speed data, then we understand that at higher speeds, if we run at higher speeds, the induced EMF will be higher, and if we run at lower speed, the induced EMF will be lower. So we have omega 2, omega 3, where omega 2 is greater than omega 1, greater than omega 3. So if we want to get the nonlinear relationship between flux per pole and field current, we can get that indirectly by doing this type of experiments, which is often described in textbooks as open circuit characteristics, or OCC, where we run the machine uh, by at a constant speed by another machine, we give some field excitation, we measure the current, we measure the induced EMF, keeping current zero, because we keep that open, and we keep on varying the field current, and we measure the induced EMF, we tabulate them. This is the characteristic of back EMF and field current at different speeds. So that is known as open circuit characteristics, to which is used to capture the nonlinearity. If we want to incorporate the nonlinear effect due to saturation in our mathematical model. So is there any question till now? Okay, so let us quickly run through the MATLAB Simulink realization of the different parts that we have discussed. So the field winding, we know that field winding is described by a series combination of resistance and inductance, where Vf is the input. So the equation is Vf equal to Rf If plus Lf dIf dt. So this is the field winding differential equation. If we want to make a MATLAB model for that, the input would be Vf, we have to subtract the If Rf drop, then we have to have a gain of 1 by Lf, we have to integrate, that will give us If, we have to feed back, multiply by Rf and get this. So this is our field circuit model. So this is our field circuit model. If we want to do it in MATLAB Simulink, this is how to do. We say that input is Vf, output is If, and we have these two parameters Lf and Rf, which we have to input as the two parameters. So this is the MATLAB Simulink realization of the field winding, right? Next we have the armature winding. We remember the equation, that is what we discussed today itself. We have the armature winding modeled as a small resistance, small inductance, and some back EMF, which depends on speed, of course, so EB, and we have LA, we have RA. So the equation goes like this: RAIA plus EB. So the model, we have VA as the input, we will have EB as another input, we have to get the IR drop subtracted, we will have to have a gain of 1 by LA, we'll have to integrate that, we will get IA, that IA has to be fed back, a multiplier will be there of Ra. This is how it will be, and this is the armature circuit model. This is the armature circuit model, where this is the armature circuit. This is the armature circuit model, where Va is the input, Ia is the input. We have another input that directly does not impact the dynamics, but it impacts the steady state value. So yeah, this is coming as a disturbance to the dynamic system. So this is called the disturbance input, and this is called the control input. Why control input? Because if we want to control the output Ia, then we will do so by changing changing Va, the armature voltage. And while doing that, this back EMF will appear as a disturbance while trying to do that. So these are the terminologies used in control systems. This is the control input, this is the output, and this is the disturbance input. So this is the armature circuit model.
Sir,
You
why
have the
it is
electromagnetic,
termed as disturbance, sir?
because it disturbs the dynamics. Does it control the dynamics?
Sir,
It
but
is
we have
dependent on what? It
expression,
is
right?
dependent on speed. Yes, come again.
Yes, yes. We have already modeled EB, right? It is function of
Yes,
some speed and IA, right?
correct. If.
Sorry, IA, IF, correct, correct.
Yes, that does not. So if is not related to this dynamic loop, armature dynamic loop, where La and Ra are the parameters of this. So armature voltage to armature current, that is decided by field winding, armature winding inductance and armature winding resistance, not by field winding current is being solved in a separate loop. It is not here, right? It has a separate time constant of this armature circuit, and time constant of field current is different. Again, that is true about speed is being solved in a separate loop, where with the mechanical time constant.
Sir, your voice
So
is becoming low, sir.
okay, so what I am telling is, this is the armature model that we are discussing, the armature loop. So the
Sir, it
armature
doesn't
system,
hold the intensity it hold previously.
is it okay now?
Bit okay,
Hello.
but not as before.
Okay, okay, that, okay, I don't know.
In the middle of
At
the
least
class,
let me.
it's good, sir. Your intensity.
Okay, is it better now?
Okay, sir, we can adjust.
Okay, so what I'm telling is, this is a system armature circuit system. So previously we have discussed the field winding system, where we have the two parameters as LF and RF, right? And the time constant of this, how if we change VF suddenly, the current VF IF, suppose IF was 0 before, it will take some time to reach steady state, and that will be first order system. So it will take some 5 time constant of the system, so 5 tau f. So tau f is the time constant of this field circuit. So similarly for the armature circuit, if we neglect or forget about induced EMF, but if we change the VA by some amount from some value to another value, if Ia was some value, it will reach the next steady state Ia value in again at a 5 time constant. So uh, that is the dynamics of this armature circuit. Now what I am telling, and again, if I do I have the speed mechanical part, let me discuss that also. So mechanical part, the equation is Te equal to J d omega dt plus b omega plus TL. So we have electromagnetic torque as the input, we have the load torque, we have the back EMF, so we have the B omega, that is the frictional torque. We will have to give it a gain of 1 by j, then we'll have to integrate it, that will give us omega m or speed, that will have to be fed back as a gain by b, and this is how the system will be. And here again, this is the mechanical plant system where this is the input, or to be specific, this is again a control input. This load is again is termed as a disturbance input, and this is termed as the output. Now what I am telling is, this torque, how that changes is not in hand of this loop of this
Sir, your intensity is very low, sir.
now is it okay?
No, sir, not okay.
Is it okay now? Is it audible?
Yes, sir, audible, sir. Sir, but in the as time passes, it's becoming low.
Okay, I don't know, it is the same. Okay, just try to focus and listen. I don't have any control over that. That is a disturbance to me. So anything, we do not have this loop cannot decide or have no control of how this TL would change. TL, the changes of TL is completely separate to this loop, but it is an input that decides the output. So that is why it is called as a disturbance that disturbs the normal dynamics. The value TL will only so if it is a DC quantity, it will only change the steady state DC output, not anything other than that. It can be time varying also, we will not go into that. But does it make sense that we have a loop going on that has its own parameters J and B that decides its dynamics? It has some mechanical time constant, but this TL, the load torque, is not part of this mechanical system, mechanical dynamic system, but it comes as an input that disturbs the normal dynamic system. That is why it is termed as a disturbance input, because it is one of the inputs, right? And the why control input? Because because anyway we do not have any control of this TL. We do not know how that will change, but we want to change the speed. How we can change? We can change the torque, that is in our hand. We can change current, and by that we can change torque. So we can change the output, we can control the output by changing this input TE. That is why this is called as control input. Is it clear now? Similarly, for this armature circuit, this back EMF, this loop does not have any information that how the speed is going to change, or the speed change dynamics is not part of this loop, but it comes and affects the uh, final output. So that is why it is termed as a disturbance input, that is back EMF here in the armature winding. And what about the electromagnetic energy conversion? If it is a linear modeling, that is, we will assume that although the flux per pole and field winding current, that is related by this type of a nonlinear uh, relationship, this is a nonlinear characteristic like this, but we will assume that it is only operating, we will think that we are limiting our uh, say we are limiting our field current up to this limit. So for this zone of current phi p, can simply be termed as a constant, say kf into if, right? In this duration where if is less than if max, where if max is this value of current. So flux per pole and this thing is related very constant quantity, constant gain. So for this case, how this uh, model will be done is, we have if coming as output of the field circuit model. Where what is the field circuit model? We remember we have the vf as the input, if as the output. This is the field circuit model. So this if will directly go, and let us have a product thing. So is if is basically multiplied by this kf to get the flux per pole. Again we have the mechanical system. We have the mechanical system that has the torque as the input, that has the speed as the output, and that also has the load torque as another input, as told, disturbance input. So these two will be coming into this product thing, and they will be there will be another term, another some constant term. So some constant k, say k1. So k1 into 5p into omega, that is the back emf that will go to the armature circuit model. Again we will, let us have another multiplier block, and the same constant basically comes here also, and we have the same flux per pole that also comes here. But here we have current that comes as output of the armature circuit model, which has the VA as input, another input is EB. So this IA basically comes here, and the output is torque, electromagnetic torque, TM. So this is the electro uh, this is, let me use another color. So this is the electromagnetic energy conversion, where this field comes as flux per pole. One input is this mechanical input, that is speed, that comes as, goes out as some electrical disturbance, back emf. And again another input, electrical input is ia, that goes in and comes out as electromagnetic torque, which is the input of the mechanical system. So if we now integrate all this, okay, so now if we want to take care of this nonlinearity, what can be done is, this block can be changed. Now we are simply using a gain block, but we could also have some lookup table based block, where this data whatever we have, that has been put, this data has been put, flux per pole to if. Now if if is the input, some if is the input, it searches in this data set, and gets the corresponding 5p, and outputs it uh, as output of this block. So this can be done to take care of the nonlinearity between if and 5p, right? This can be done to take care of the uh, nonlinearity. Now just to integrate all the things, we have the complete DC machine model. One input, one thing is the field circuit model. We have the field circuit model, whose input is the field voltage, and output is the IF. Now we have the armature circuit model, whose one of the inputs is VA, another input is EB, and output is IA. Another model is there, the mechanical system, whose input is TEM. Okay, that is some internal thing, so let me show it with smaller one. This is TEM. Another input is load torque, and the output is speed. Now this EB and TEM, how that comes, that depends on electromechanical energy conversion block that takes the field current, that converts. So either it can have a characteristic like this, phi p versus this thing, so it gives the phi p, and this phi p again, now it's a product thing. So we have one of the inputs coming as armature current IA, we have another thing, so this is the multiplication block, one of the inputs is this, we have another multiplication where we have the phi p coming, we have the omega m coming, and what goes out is back EMF. And this is the model, this is the EM energy conversion model. Its output is TEM. So now if you see, if I draw the entire thing, so this is the entire DC machine model. This is the entire DC machine model where the control inputs are VF and VA, the field winding voltage that we can control, the armature winding voltage that also that is in our control, load torque, that is what we want, that is not directly under our control, but uh, so that depends on the speed also. So the load torque and speed, they are sometimes dependent for certain loads. So what are the outputs? One output is surely that we can measure is the field current. Another output is surely the armature winding current, that also we can measure. Another torque is not directly measurable unless we have very high end torque transducers or something, so I will not consider is as input or as output, but we can measure the speed also, the omega m can be measured. So this is the DC machine model, a DC machine model where the inputs are VF, VA, the outputs are IF, IA, and omega m, and this depends on the torque, load torque, how that varies. Now the load torque, as I have discussed before also, we can have different types of loads, and the load torque, different types of load torque versus speed characteristics. So say a fan, a blower kind of a load which needs to the rotation requires some torque, and because of the aerodynamics it comes out that whatever load torque a fan requires, that is proportional to the square of speed. You can have several kinds of torque. If it is mostly a frictional load, then it can also be load torque proportional to omega m. or it can be nonlinear, some other kind of function of speed also. So let us consider one of them. Say fan load is a common load, so where TL is some constant KL times omega m square. So if we have the DC machine model, say this is our DC motor model, where one of the inputs is Vf, another input is Va, another input that is required is the load torque, and one input is field current, sorry, output is field current, another output is armature current, another output is omega m. Now this load torque is related to the speed that at which we want to run the motor. So say they are related by this relationship, TL is equal to KL into omega m square. So this TL can be obtained by first taking a square. So let us take a squared operation, then let us take a multiplier operation, so KL, and whatever is the output that goes as TL. So this is one of the ways to model a load if we want to run simulation of a complete DC machine plus load model, where Vf Va are the inputs, If Ia are the outputs, and omega m is the output, and omega m and TL are related by this load characteristic. It could be anything. Again, instead of a mathematical relationship, it could be uh, some curve, some load torque versus omega m, which could be some points also, which could be anything. So this data could be put here, and a lookup table based system could also be employed to solve a similar system. Okay, so here I conclude this discussion on the dynamic modeling of the DC machine. Is there any question on this part, whatever I have discussed?
Sir, what is the physical meaning of the equation TL is proportional to omega m square? Does it means if I want to run my load at a certain speed of omega m, it demands a torque of KL into omega m square or
Yes,
something else? Could you please
yes,
explain the physical significance behind it?
that is what it means. Suppose you want to suppose the load torque characteristic is something like this. So TL omega m square. Now uh, this is how it will be. So it means that if you want that load, say some fan type of load, if you want to run that fan at this speed, say omega 1, this is the torque it will require, say TL1 for omega 1. But if you go to higher speed, it will demand a higher torque, TL2 omega 2. So it tells you that for running the load at a certain speed, how much torque will be demanded out of the motors.
Okay.
So it
Sir,
has some
here,
physical, it has some for fan type of loads, it is a basically it basically comes from physics. It comes from aerodynamics or some equations. I do not want to go into that, but you can refer to it, how aerodynamic loads are or fan type of loads, why they are of this kind of nature, why square of omega m. It comes from physical equation relating aerodynamics.
okay. Sir, here, what is the independent variable and what is the dependent variable, sir?
Uh, Independent means which do not depend on something else,
Yes, correct.
and dependent means the variables which depend on some other variables.
Correct.
So here, because the voltages Vf and Va, They do not depend on something else.
No,
That
sir. Sir,
whatever
I'm
voltage
just.
we apply, that is the value that does not depend on anything else. But Ia and If and omega m, they depend on something else. They depend on what is the Va, what is the field voltage we have applied, what is the armature voltage you have applied, what is the load torque. So all these things are, the outputs are basically dependent variables, or the inputs are the independent variables. Or yeah, these two inputs are the independent variables. Because this again, TL also depends on speed.
Yes, sir. I am asking among TL and omega m only, sir.
Among TL and omega m, so TL seems to be dependent, omega m is the independent, because TL is what depends on the omega m.
But
But
to
dependent
sir,
independent, that is not very important in terms of control and other things. So what do we want to control, that is more important. So what is, which variables or outputs are measurable, which we want to, which have some physical significance and we want to control them, those are the control, those are the output variables. Output variable, I think, is more relevant compared to dependency and independencies.
okay. Sir, basically what I have struck at here is like to run at a specific omega m, I'll need this TL low torque, or if I have this much of low torque, I will run at this omega m. That is the confusion I'm having.
That is okay. It depends what is the end goal. You want to run at specific speed, or you want to deliver certain torque.
Okay.
That is about, both are interdependent. Nothing
Yes, sir.
is
Yes.
completely independent. We cannot independently control speed. We cannot independently decide what is the load torque. They are dependent. They are basically interdependent. But independent variable means which are not dependent on anything else. That is like VF VA, which
Yes,
if we
sir. That
decide,
is
if we,
clear.
yeah, they do not
That is
depend on
clear, sir.
anything else. Yeah. Okay. Anything else, or shall we close for today?
Yes, sir. We can close.
Okay. Thank you.